Hi, everyone. Thank you very much for coming. I know we still have a bunch of people coming in. We've got so much material to cover. I really want to make sure we get started on time. Thanks also to everyone joining on the live stream. We're going to talk about Canary deployments using Istio and Kubernetes with Spinnaker or other tools. My name's Andrew Phillips. I'm a product manager in GCP working on continuous delivery.
And I'm Nora Lutz, site reliability engineer at Descartes Labs. But I like to say that I'm a recovering systems admin. I've been in this industry for just under 10 years. Got my start in high-performance computing and research at Old Dominion University. Around 3 years ago, I moved into geospatial and Earth observation at NASA. And it was around that same time I started working within the Kubernetes ecosystem. So now I'm at Descartes Labs, and I'm really excited to share some of the stuff we'll be working on.
Thanks, Nora. So let me briefly give a quick overview of what we're going to try and cover today. I'm going to start with a quick introduction to what's the actual challenge, what's the problem we want to address. I'm going to do a very quick recap of what Kubernetes also offers out of the box for application rollouts. We're going to use some of those options to talk about a pattern that you can use to implement Canary Analysis. We're going to talk about what you get if you add Istio into the mix, some additional options. And then we're going to stop with the theory in my slides, and Nora's going to talk about what this actually looks like in practice at Descartes Labs. Just a quick reminder, if you have questions, you can post them in the dory. There's a link in your app that you click, and feel free to post them there at any time during the session. We've got a lot of material. I hope we'll have time to answer the questions. You can also ask questions live. I think there's a couple of mics around. We'll try and alternate. We'll try and get to as many of those as we can. So let's start by briefly talking about what the actual challenge is that we want to solve here. I think we kind of all roughly know deployment is all about moving fast without breaking too many things. So we want to roll out new versions of applications. We want to do that safely. It should be easy. We don't want people to have to follow a 12-step kubectl guide or whatever. It should be reliable. Ideally, it works well when you do it, but also if something doesn't quite work as expected, you should have good fallback options. And then, of course, in an ideal world, we want it to be aligned with whatever is considered best practice. And if we're talking a Kubernetes environment, a lot of that revolves around how can we do this in a declarative way where we focus on our intent rather than exactly the details of how we're trying to roll that out. So just high level, what's the scenario that we're talking about here? Nothing particularly fancy. And in general, I should say, the main aim from my perspective, we're not going to talk about magic here. Most of you may know all the things that we're talking about here. It's more about representing a pattern so that you can take away with some guidance and some confidence. But the overall scenario is that I've got version X of my application. It's running somewhere. We'll assume it's serving web traffic. Most of what we're going to talk about applies equally well to applications that do things like processing messages off a queue. But for the purpose of the diagrams and so on, we'll assume that it's a web-serving application. And then you've got a new version Y coming out of your build process or your CI process, and you want to switch your users over to that application. So at a high level, the sort of simple diagram is you've got a load balancer of some sort. You've got a running version of your application, V1 in this case. Magic happens. Everything is safe and reliable and wonderful. Ta-da! We finish with version 2 of my application running. That's really, in a nutshell, all that we're going to talk about, how to try to make this work really well. So a quick recap, what does Kubernetes already give you out of the box? Most of you are probably familiar with the deployment object. Specifically, if you look at the rolling update strategy of the deployment object, there's already a pretty good option for out-of-the-box magic, if you like, as we just saw in that slide. And what you get with a deployment object is what we might call a rolling blue-green cutover. Talk about that a little bit in a second. And there are also some useful controls that you have to handle how much over-provisioning of new resources you want and how quickly you want the old resources to die away. Specifically, there's two parameters, max surge and max unavailable, that you can use to tune this. So there's already some pretty nice options. What you get is a picture that looks a bit like this. You've got a service. You've got your deployment object, which is managing a replica set. It starts out here. You decide to switch to V2, spins up a new replica set, adds new pods, more, another one, ... Finished. So that's what you can do out of the box. And the parameters control how many new ones you spin up, how quickly the old ones go away. So what's good about this? Well, I guess the best thing, it works out of the box. You can pretty much do this without any real effort. You have stable naming, which is nice. It means that the resource name, if you like, that your application workload refers to is the same, like even v1, v2. That's not part of the name. You can just pull in your workload. And you don't need to do anything low level, like managing labels. It just works. But there's also some limitations that come with this. And when I say limitations, I should be clear. This can be perfectly fine for 80, 90, maybe 100% of your use cases. So just because there are some things you can't do with a deployment object absolutely doesn't mean that it might not be good enough for everything that you need. But for example, one thing that is not that easy to do is when one of your new versions comes up, you can't really get in there and manipulate it very well before it actually gets traffic. You can play a bit with a health check, but it's not that easy to control that in a fine-grained way. The traffic cutover process, it's kind of baked into what the deployment object does. Like as the new pods become healthy, they get traffic. You don't have a lot of fine-grained control about that. And also in terms of fallback options. Like once the deployment has happened, and if you don't like the way v2 is behaving, you kind of got to do the process in reverse to go back to v1. You can get the old revision, but for example, you don't have a running instance that you can quickly switch traffic back to. So if we need some more flexibility here, we can do some things that are a little bit more fine-grained than what the deployment object provides. And so we're trading a little bit more effort on our part to actually make this work with more flexibility and more options that we have. So as an example, we can do a full blue-green deployment. I'll show a diagram in a second, which is not a rolling blue-green, where we get the whole new application running, and then we can do things with that, and then we can switch traffic over. For example, we can use that as a pattern to carry out more extensive validation of the new workload before we decide to expose our users to it. So at a high level, might look something like this, right? So you've got a load balancer, you've got your current version of your application running, you spin up the new version, so now you've got this thing sitting there in a sort of dark launch pattern where it's not getting any traffic yet, but the app is running, it's warmed up, you can run things against it. You decide it's good to switch your traffic over. Now your users are using the new version. But you still have the old version around, which is useful. Imagine your apps take a while to boot up. If there's a problem now, you can easily switch traffic back to the old version, and those apps will serve traffic straight away. You wait, and then you can have this standing around for a while, and eventually, when you're confident that the new version really is good, then, of course, you probably want to get rid of the old resources so that you don't have them standing around forever. I actually have some wonderful slides, well, I think wonderful, that talk about how to do this in detail with Kubernetes. We don't have, I think, enough time to cover them today. If you're interested, please come up and see me afterwards. So that gives us one pattern. But if we need even more safety than this, so there's a few things that can go wrong with this pattern. We can use that blue-green pattern that we talked about, and instead of just switching traffic over when the new app is running, we can decide to perform some more tests. We can run a suite of integration or performance tests, or even allow a set of limited users, our internal friends, or maybe a set of EAP customers to hit the new version of the app. We can do a sort of manual, a very slow rolling update, if you like. So if you go back to the picture, rather than bringing up all the new instances, we can bring up a few, and then we can switch traffic over, and we can slowly increase the amount of instances that serve traffic, and slowly decrease the old version. And that's it's basically what the deployment object does, but we can control the stages in which that happens. Or we can do a canary rollout, which is another pattern that allows us to inject some more safety into this process. So I think most of you will have heard of this term before. I'll define it for the purposes of this discussion. What is a canary rollout? Well, it's a way of evaluating a candidate version, which is the new version we want to deploy, against a baseline, which is related to the currently running version most of the time, to check for unexpected deviations of behavior. So this is not about functional testing or something like that. This is not about checking whether the new version does what you want it to do. You have a new feature, you want to make sure the feature works. No. It's about verifying that the new version behaves acceptably, whatever that means, with respect to the existing version. So for example, the CPU utilization doesn't go through the roof, or something like that. And this is useful if the application's behavior across the metrics that you're measuring is not expected to change a lot. Of course, there are types of changes. Imagine you've added a CPU fix where you're expecting the application's performance to behave quite differently. And so as part of your analysis of your canary to figure out whether you should go ahead or not, you need to be able to take these kind of expected deviations into account as well. And Nora's going to talk a little bit about some of the ways in which some of the things that you can do in your canary analysis to make this work. So what's the schematic for a canary rollout? Well, you start with a load balancer. You've got your current app running. And then you move to this intermediate state in which you have your current running app, and you have a baseline, and you have a candidate. Why the baseline? It's very common to see what I might call simple canary approaches, where you just compare the candidate with the existing version. And that's OK, but it's really not an apples-to-apples comparison. To take a simple example, the baseline, or the original version, is serving much more traffic than the candidate. So it might behave differently just because of that. It's also been running for however long it's been running, whereas the candidate has just booted up. And so if you want a proper side-by-side evaluation, you should have a baseline that matches the candidate as closely as possible. And that means it should serve the same percentage of traffic, and it should have been spun up and configured in roughly the same way as the candidate. So you run this for a while. You decide if you want to go ahead. Great. You can get rid of the baseline and the old version and just switch all the traffic to your new version. And I'm glossing over how that evaluation process happens. Nora's going to talk a lot more about some tips and tricks about how to get that right. Or if it doesn't work out, you decide, OK, that wasn't a good idea. Goodbye baseline, goodbye candidate. And then we're back to serving traffic with the old version, and we try again. So how do we do this with Kubernetes? Vanilla. We can use label selectors on the service, and we can use appropriate sizing of our baseline and our candidate to approximate the traffic distribution that we want. We could use all kinds of, we could use replica sets, for instance, but we would recommend using a deployment object for the workload, just because that's the thing Kubernetes uses for these kind of workloads. And for consistency with the way the common deployment object works, we recommend that if you do decide to go ahead, instead of switching traffic over to your candidate, you actually just update the existing deployment object in place. So that way it looks just like a regular update if you weren't using Canary Analysis. So what's the schematic if we're doing this with Kubernetes? We have a service, we have a deployment, we have some label selectors that are pointing at the current workload. I'm using the conventional ones. They're useful. You might want to use your own. That's not a hard and fast recommendation. Notice that the label selector here is quite specific. You'll see why in a second why it has this component equals server additional selector, because as we move into the intermediate stage, where we have 3 deployments all of a sudden, we obviously have to loosen the label selector so that it hits all 3. Label selectors on services don't support the set-based selector, so that's how we're going to do this. And now we have traffic roughly distributed across the 3 different deployments. And so that's where the sizing comes in. We have 6 and 1 and 1, and that gives us roughly this distribution. I say roughly because that's really heavily dependent on the characteristics of your load balancer, of your service. So don't assume, just because the sizing, the math of the sizing works out like this, that that's what you're going to get. If you want to do vanilla Canary with Kubernetes, we highly recommend that you run some experiments to figure out whether you're actually getting this kind of traffic distribution, because load balancers have lots of intelligence built in that might make this different. Well, I should say one quick thing. One thing that you need, in order to spin up the baseline here, you need access to the deployment configuration of your current app. And so that means that you have to get that either from the runtime or from a GitOps repo or whatever you have. It's not just the new deployment object that you need to spin this up. All right, I need to speed up here. So we decide to go ahead, great. We narrow down the label selector again. We update the new version. It does its rollout. 1, 2, 3, wait, done, wonderful. So now we have our Canary deployment finished. So if we need more sophistication, this works. And you can do vanilla Canary with Kubernetes as this pattern. But if we need some more sophistication, we noticed there were already some, well, a little bit of, so I wouldn't say friction, but the sizing was already a bit of a challenge. We can use Istio to do more things here. Istio is a service mesh. Heard a lot about it. It has many more features and many more use cases than just traffic distribution in a Canary rollout. But it's a very useful thing to use if you're interested in doing a more sophisticated Canary too. So there's two main things that we're going to talk about today that are useful. One is that it supports fine-grained traffic splits, and the other that you can do content-based routing in your Canary as well. I think that's a bit of an advanced topic. It's not everyone has to go away and implement that, but it's nice to know that it's possible. So there's two Istio resources that we need to know about if we're going to use it like this. There's the destination rule, and this defines subsets. So that's resources to which traffic should be sent. And then there's the virtual service, which defines the routing. Basically, match rules that say, under these particular conditions, take the traffic and send it over to these subsets and send this much of the traffic. So in practice, a subset of the YAML looks a bit like this. Over on the destination rule, you have a subset called myapp, same label selector we used. And then over on the virtual service side, you have a route that says, take all the HTTP traffic and send it over to subset myapp. And so the picture looks quite similar to what we had just now with Kubernetes. You've got your destination rules up there. You've got your virtual service. It has a subset. It's sending all the traffic over here. And now we add the two new deployments. That's outside of Istio. That's just regular Kubernetes. But now we add this YAML to our Istio configuration. We define two new subsets. Oh, it's much more legible up there than it is here, which is nice. We define the candidate and the baseline, and we use label selectors to point specifically at those. And then we add a weight distribution over on the virtual service side, which says that we're going to split the traffic 95-5 in this case. So we end up with a picture that looks a little bit like this. And notice that we can have a traffic distribution here that is different from the sizing of the individual replica sets, which is really nice. So one of the nice things we can do, if you only have 5% of traffic on your Canary and your baseline, it might take a while to get enough data to make a good Canary decision. You might not want to wait that long. So as you've gained a little bit of confidence that your Canary is doing well, you might want to ramp up the traffic. And you can do that really easily with this kind of configuration change in Istio. And then, again, without changing the sizing, you now have 80-10-10, which is nice. One important point to bear in mind here, as you decide to ramp up more and more traffic, you pretty much want to make sure that you have a horizontal port autoscaler on those replica sets, because you don't want them to fall over as you send 50% of traffic or 40% or whatever to your Canary and your baseline, or your candidate and your baseline. So now if we decide to go ahead, great. We can get rid of the subset definitions, and we can change the weight distribution back, and we can update the deployment object, and then we make that change. And as before, it goes through its regular deployment pattern, and we're done. We now have version 2 running. We've done a nice Canary rollout with Kubernetes and Istio. So to add this little kind of funky advanced topic into the mix, imagine we have some really critical customers, and we're really, really concerned that they should not have a breaking application on them. So we really want to make sure that they can, when we do a candidate evaluation, they don't get sent to the old version, or the new version rather. So we can do content header-based routing in this case to do that. I'll skip through this a little bit. You can define a match rule that matches specifically on the header, and you can say, under these circumstances, always send to my old subset. Am I missing a slide here? No, always send to my old application. And one thing that is obviously worth bearing in mind, that if you have these kind of rules, the traffic distribution, that's what that little star is, changes a little bit, because of course, the people that match this specific condition are going to the old version, and so you end up with 95.5 of the remaining traffic. All right, quick overview of the recommended pattern that we talked about here. In the steady state, you only need to keep the running version of your application using a deployment object. When you start your rollout and you want to do a Canary, you create two new resources, a candidate and a baseline. And you use the deployment config of the existing version for the baseline, and you use the deployment config of the new version for the candidate. You add subsets to your destination rule and appropriate weight distribution to your virtual service. It's useful if you're automating this, if you think of the weights as parameters to your automation scripting or your automation tool, because that makes it easy to do a multi-step canary. You can easily go from 80, 10, 10 to, or 90, or to 60, 20, 20, something like that. And you should definitely use a horizontal pod autoscaler for your baseline and your candidate so that they ramp up as the traffic comes up. So then you wait, gather data, and then you make a decision. If you're good to go after the Canary analysis, you just update the deployment that represents your running app and get rid of the rest. And you can remove the subsets from the destination rule and the weights from the virtual service. And of course, you can get rid of the candidate and the baseline workloads. There's lots of shortcuts possible here. You can, for instance, keep the candidate and the baseline around and have them spun down. And that means that your YAML changes might be a little simpler. But this is the sort of cleanest and nicest approach because in your steady state, you only have one running workload, and everything else is ephemeral during the course of the rollout. So, speed up a bit. This could be an entire talk in its own right. One thing worth pointing out here is that the rollout that we looked at represents a sequence of 6 or 7 config changes. And if you're thinking of a GitOps-style pattern where you want to capture the intended state of your runtime in a repo, the question becomes, how do you reflect these config changes in that repo? Clearly, you don't want to have your users do kubectl 6 or 7 times as you're doing this Canary analysis. So automation tooling really should be updating this repo. Another approach that we see some of the community tooling take is to basically hide this kind of canary pattern inside the CRD. So you post something like a canary rollout, and it magically makes all the resources for you and runs however long it runs. That's possible, but one of the things it does is it means that your repository doesn't really reflect the actual state of your cluster very well, because you think you have one deployment, but you actually have 3. And so we think having your automation tooling make these updates back into your repository is a good mix between making it simple for the user, they just need to say deploy with Canary, and between having a representation of your actual cluster state so that you can see at any given time what was really going on. One more. Yes, so a final summary here. 3 main takeaways from my side. You can implement Canary rollouts and other strategies that go beyond the vanilla deployment object in Kubernetes. You can do that pretty easily using vanilla Kubernetes resources, or if you want more sophistication for canarying, you can use Istio, add that, and it gives you at least two nice powerful features, including traffic shaping and also content-based routing. And then if you want a recommended sequence of config changes for your resources as you want to do a Canary rollout, well, we have one in the slides over here. You can easily automate this set of config changes using Spinnaker, as we'll see right now, or indeed a bunch of other tools. And now, to actually see what this looks like for real, let's hand it over to Nora.
Thanks so much, Andrew. Awesome. A lot of great information. Thanks so much. So before we get into our demo here, I want to talk just really quickly about who Descartes Labs is, what we're doing, why Canary rollouts are actually very important to us. So at Descartes, we're focusing on building models of the physical world, right? Things like agriculture, supply chains, transportation, energy production. 4 years ago, the founders spun out Descartes Labs from the Los Alamos National Laboratory after incubating their underlying machine learning technology for many years. So then we took that and built a software as a service platform on top of GCP that our customers can leverage to build their own machine learning models, utilizing petabytes of remote sensing and geospatial data. So to comprise this platform, we use about every GCP product available, I think, except for maybe exception of App Engine and Spanner. So here's one quick example of how we build these models. This is a natural color imagery of farmland in Greenfield, Iowa, taken from Sentinel-2. And here's that same imagery after going through our pipeline. So our platform has empowered our applied scientists to segment up that imagery into boundaries of towns, fields, roads. We then took a machine learning classification model on just the fields to show corn and soy field boundaries. And then we took that a step further, and we were able to use the non-human visible spectrum of light and seeing how it travels through the plant to see how much fruit the plant is growing. And then we scaled that up using Kubernetes, using hundreds of thousands of cores, tens of thousands of pods. So we can view this growth every single day on every field everywhere in the United States. So why am I up here talking to you about Canary releases, right? Obviously, DevOps is not our core business model, but we needed to always be improving our feature velocity, right? We needed to move faster. We needed to add new capabilities and continue scaling up our platform. But we wanted to do this without introducing issues that have cascading effects across our complex interlocking services. Detecting problems when new features are released to production is actually pretty hard. But what if we could have a way to detect them before they went truly live? And we wanted to do all of this with minimal human intervention, right? Humans are good. Humans are great. Engineers with lots of operational experience are wonderful. But they're not infallible. To be able to sustainably meet our goals, we needed a nuanced and fully automated approach. So these are some of the circumstances that led us to investigate tools to do things, help us do things like Canary Analysis and Canary deployments. What we found when we were trying to solve this problem can kind of be split into three main categories. I'll briefly go over those. We looked at things like continuous delivery. We looked at tools like GitLab, which is a very mature delivery system that required a lot of buy-in into their ecosystem. We also looked at a lot of things like Jenkins scripts, which seemed a bit heavyweight for our use case, kind of like bringing a chainsaw where we needed a scalpel. And also the story to implement canaries was not as clear at the time we looked at it. And then finally we looked at Spinnaker, right? Which is an open source project spun out of Netflix, for those not familiar. It has a feature-rich Kubernetes v2 provider that supports complex pipelines, consuming and producing Kubernetes native objects. And helpfully, it also supports Canary Analysis through something called Kayenta. And then next, we're looking to get those metrics to be able to do our Canary Analysis. We needed to be able to do those fine-grained traffic splits. So lucky for us, we're already using Istio in production. So we didn't have to look very far there. And then finally, when we looked how to actually implement this in practice, how to do these Canary analyses, we actually, at the time we looked last year, didn't find a very consistent pattern or best practices guidelines as reported by the community. In fact, what we did find at that time was a lot of conflicting approaches. And so, of course, here today, I'm going to introduce one more approach for you all to consider. So here's what we use at Descartes to power our continuous deployment pipelines with canaries. My hope is that you're going to take away some ideas and concepts on how this can work at your organizations. So we have Spinnaker with Kayenta for Canary Analysis. We have Kubernetes. Our Kubernetes is all run on GKE. And then finally, we have Istio. So before I hop into the demo, I want to show you where we're starting from. Like, what is the current state of affairs? We have our service here, Tiles. This is a real service that we use to scale up analysis over large geographic areas by splitting them into a grid of smaller sized tiles. We have our deployment object, our service object. And then we have our Istio virtual service tiles release, which routes all of our production traffic to our Kubernetes service. And then finally, we have our ingress gateway, which is receiving and routing all of our traffic coming into our service mesh. So what we're going to try and do today is update live to production a version 2 of this app right here on stage. So let's go ahead and head to the demo. All right, perfect. So here we have our Spinnaker UI. Now don't worry if you haven't seen this before. It's a lot going on. And then come talk to me after if you want to talk more about the details of this. And we're going to spend a lot of time talking about the intricacies of configuring canaries for analysis. So I'm not going to spend a lot of time on Spinnaker concept as much as how you fine-tune your canary analysis, because it's not just magic. You know, I'm going to pull back the curtain. It's actually pretty nuanced. So anyway, let's move on. In our case, we're using the version 2 provider, right, which allows us to manage many of our Kubernetes kinds, deployments being one of those, and also Istio kinds. Most relevantly to our discussion here is going to be our virtual service. We have our application, Canary, which isn't actually a one-to-one mapping with tiles, but it does contain our pipeline that we're concerned about here, which is our next demo canary pipeline. So if we click through, we can see that our pipeline contains artifacts, parameters, and stages. Stages consume those artifacts and parameters. Some of them are Canary Analysis stages. And in our case, let's go here. The artifacts we're concerned with are for the tile service itself. So we have our deployment manifest captured in GitHub. We have our virtual service. And then finally, we have our tiles image, which is in GCR. So let's finally just jump into it. Let's kick off the pipeline. I'm going to start a manual execution here. And I'm going to supply an image tag, which of course is now not copied because my computer turned off. Thank you, demo gods. So we supply this as a parameter to bind to our correct image in GCR in our deployment manifest. Normally, this pipeline would be triggered by a pub sub, right? So when a new tag is made available, the tag would then be sent to Spinnaker as part of the payload. So let's talk a little bit about these stages as they start to run through. We have our get image from production stage, which produces an artifact, namely our tiles image that's currently running in our tiles release deployment version 1, right? So this is what Andrew talked about. You need to get the image that's running in production to be able to feed that to your baseline. So that's a pretty critical moment. This is going to be consumed on the next stage. So now we have our canaries and our baseline being deployed. Canary is going to be deployed with the candidate release image tag, baseline with the image tag that we obtained from our previous stage. Something to note here, baselines and canaries are using identical horizontal pod autoscalers, deployments, and service objects, right? So this helps us eliminate variations that could affect adversely analysis results. So once those finish deploying, our virtual service is going to be updated for the first time to shift a percentage of production traffic away from the production release and towards the Canary baseline pair. So we're going to start by shifting 10% of traffic to each of the Canary and baseline services and keep 80% running to our release. We have several stages in our pipeline that manipulate the virtual service for tiles release so that we increase the weighting as we go, so more and more traffic heads to Canary and baseline. Something I think is worth pointing out here is that instead of maintaining and versioning a virtual service manifest for each and every of these combinations, we're parameterizing this using something called Spinnaker expressions. And these are going to be evaluated during each stage. So let's go back here and, all right, so at this point, our virtual service is been templated out and deployed. And we're going to move on to our first Canary Analysis stage. So this stage is powered by Kayenta. This is a Canary Analysis service released jointly by Google and Netflix that aggregates and compares metrics for judgment whether a canary is healthy relative to a baseline. As I mentioned, this is now integrated into Spinnaker and can be enabled. I'm not going to go into that here, but it's fully documented, and we're happy to talk about that later. So there's two main areas of configuration when it comes to Canary Analysis, and the first is our Canary config. So in our Canary config, we're going to specify metrics that we want to compare between a baseline and a canary. Not shown here, but actually very relevant to this, is our telemetry provider, right? We can't compare anything if we don't have metric information. In this case, our Istio metrics are being exported to Stackdriver, right? So we're going to use Stackdriver for our use case, but you can also use things like Prometheus, Datadog, and others. So what metric do we actually care about for tiles? What do we want to analyze when we're trying to add a new candidate release? Response latency to client requests is one metric that's pretty important, right? We want retrieval of tiles of rasterized data to be quick so as not to impede higher level analysis. So let's go ahead and click into that metric. We should think of these metrics as a set of templates, right, that are going to be for queries that are going to be executed against your telemetry store for both your baseline and your canary. We're going to define failure depending on whether the canary metric is seen to increase statistically relative to our baseline. In this case, we want to fail if the response latency is higher coming from the canary. We chose a resource type that represents a set of time series data that we want to measure, in this case, Kubernetes pod. We then need to choose a metric type that has data specific to this resource. So Istio exposes all sorts of great metrics right out of the box that you can use. In our case, we're measuring client round-trip latencies. And so this is a distribution of latency values. We then want to use things like grouping and filtering to further refine these data points that you want to compare, right? Being able to get that exactly the right data that you want to compare is actually part of the biggest part of the nuance here. So we're going to filter out unhealthy responses, anything not a 200 series response. In other metrics, you may care very much about whether or not it's healthy or unhealthy, but in this case, we want to consider healthy responses. We want to filter on the destination workload name, which is going to resolve to either tiles baseline or tiles canary. Remember, these are templates, where our namespace is tiles, and a request is a post. Because in this particular execution path that we're testing receives post requests. And then we're going to take that and actually clean that up and aggregate that a little further. We're going to help smooth out this distribution for better comparison using aggregators, aligners, and reducers. So we want to choose the 50th percentile value of each latency distribution as a single data point for the whole period of 1 minute. And why do we do this, right? One of the reasons we do this is we want to safeguard in our analysis against things like a random expensive request or a series of those, network failures, things like that. They don't creep in and accidentally cause false negatives and positives. So by aggregating this data, you're going to be able to have a more apples-to-apples comparison. So let's go back here. If you do choose to analyze more than one metric, which is probably recommended, these can be grouped, and those groups can be weighted in importance. One example of why you might want to do this, in our case, we chose latency, but if we also had error rate as one of our metrics, in this scenario, latency metric analysis shows that it's near identical performance between canary and baseline, and so the analysis is successful. But error rate is significantly higher in the canary. So that should probably be weighted higher, as it has much more severe implications for your service health and for your customer experience. And then finally, I'll briefly touch on scoring thresholds. So our marginal score is the minimum value that a canary analysis can have and still proceed on to further analyses. And our pass score is the minimum score value that the final analysis should have in order to pass for the entire stage. In our case, we're only measuring one metric, so it's kind of a binary operation, right? Either you failed, 0, or you passed, 100. So we set our scores to 99 and 100 respectively. So the second piece of this puzzle is the analysis stage itself. In the stage config, we want to specify how Kayenta is going to operate for this particular analysis stage. Right? We're going to set our analysis to real time to measure our deployments that are running right now. But you could also set this to retrospective. Right? So if you have a canary and baseline pair that have been running in the past days, the past weeks, the past months even, you could have this do the exact same analysis over that period of time. But for this demo, we set real time. We set our config name, but I think the most important value to set here, the most important thing to think about, is the lifetime value, right? Currently we have it set to 3 minutes. Not a very long time. That's for this demo. And I'll go into why this is so important. In order for your comparison to be accurate and not reflect more potential false negatives or positives, you want to set a long enough lifetime to gather enough data points to ensure that anomalies don't skew your analysis, right? So you want to set a long time to gather this data. We also set our baseline and canary namespace and deployments here. So after our analysis run is complete, we can view our analysis report once Spinnaker loads. So in this amplitude versus time chart, let me zoom out a little bit so you can see all of this at once, hopefully. In this amplitude versus time chart, you can see that the comparison of time series data we filtered out from our Istio client round-trip latencies metric, right? So it looks like our Canary is not introducing statistically significant higher latency than the baseline, and so our analysis is successful, which is great. You can also view things like the maximum, minimum, and average latency data points gleaned from our 50th percentile time series. And if you actually click through here to your metrics, you can see all of your data points that were gathered throughout the lifetime. But you're probably thinking, well, Nora, this doesn't look very impressive, right? It's 3 data points, right? And this actually highlights one of the issues with such a short lifetime. With a period of 1 minute and an analysis lifetime of 3, that only allows for 3 data points to be aggregated. With such a small sample size, analysis results may be less than representative. So it's very key that you spend enough time gathering this data on the order of hours and days, not just minutes. So now that our analysis is successful, we're going to move on, the pipeline's going to move on and increase the weights to our Canary baseline pair. So we're going to, let's go ahead and head back to the slides real fast. So at this point, we're starting to adjust our weights, right? We're updating that virtual service to set our traffic to 20, 20, and 60. And as this occurs, our traffic, and thus the CPU across each deployment, is going to increase. And so our horizontal pod autoscaler is going to begin to scale our tiles, baseline and tiles release as a function of the load. One of the ways to visualize this is with Stackdriver. Here's a chart I created to view the current numbers of tiles pods as reflected by their CPU request counts. You can see our release deployment scaling up and down as a function of traffic, while our Canary and baseline are also scaling up to meet the demand as virtual service weights are increased. So eventually, our virtual service will have weighted the Canary and baseline to receive 80% of traffic. Right? So we're pretty confident at this point we've got a healthy release. And then we're going to perform the final analysis, currently using our same config and stage parameters as before. The reason you might do multiple analyses is because behavior is going to change as your candidate scales up, right? As you scale, it's going to introduce potential issues, things like memory leaks or a slow burning bug, that sort of thing. So having multiple periods as you scale is going to give you more confidence that your candidate is actually healthy. So if that's successful, our release deployment is updated to use our new tiles image tag, version 2. And then we're going to begin reversing this weighting process, letting our tiles release deployment scale back up gradually as it receives more and more of the traffic again. This is so we don't shock the system, so to speak. As our release has scaled down, if we reintroduced 100% of traffic, that could have a spike in latencies, failures, unpredictable behavior. So we want to start scaling down our baseline first, because this is the oldest deployment at this point, and scaling up our production release. Then we scale down the Canary until we have our successful release. It's important to note that regardless of success or failure, the Canary and baseline deployments are deleted, and tiles release is reset to receive 100% of traffic via our virtual service. This is implemented by another pipeline that's triggered after the previous is completed or failed. So to wrap up, here's some pro tips I can give you guys when you're looking to implement this yourself, right? Choose metrics that reflect key service health indicators, right? So if your candidate release was to go into production, choose what you would care to measure. If you already have things like service level indicators, have those established. It's a great starting place. Accruing a large enough sample size and aligning the data for apples-to-apples comparisons is critical to avoid false negatives and false positives. Having identical baselines, canaries, and releases, except for image tag, helps ensure that you're examining the right difference between your service instances. Change one variable for your analysis. And I didn't go over it very much, but every deployment, horizontal pod autoscaler, service, and virtual service was fully parameterized with Spinnaker expressions. This meant I can avoid having to version potentially hundreds or thousands of manifests and dynamically populate them at runtime with Spinnaker parameters. This is a really powerful feature of Spinnaker and should absolutely be taken advantage of. And then finally, the way Kayenta interprets these metrics labels from Stackdriver is a little bit opaque. So since we're using Stackdriver, I personally found that using the Metrics Explorer very, very helpful in teasing out those mappings. So take advantage of the tools that your metrics store provides to help you get this right. So Canary Analysis and CD for Kubernetes is an ever-moving target. We want to work with you guys, the community, to help shape these patterns and tools. I'd recommend checking out the Spinnaker Kubernetes Special Interest Group and the hashtag Kubernetes channel on Spinnaker Slack to join in. And then finally, a little plug. Come check us out at descarteslabs.com. If you're interested in using our platform to power your geospatial machine learning models, or just curious about what we have to offer, check out our APIs at docs.descarteslabs.com. And if you also have a love for geospatial data, modeling the Earth, want to solve tough engineering challenges, check out our jobs page, or just shoot us an email at hello@descarteslabs.com. All right.
Thank you, Nora.